Hey, gosh, I hate that. That one almost kicked my ass. Hello, everybody. Hi, Ben. How are you doing?
Hey,
Google
well,
wanted me to reauthorize myself right in the middle of talking to myself. I never get used to that. How are
question.
you?
Can you
Yes.
see me? Because I cannot see you.
I can see you. You're fine.
Okay, somehow your Skype isn't taking its feed from XSplit.
Oh, wow. So you can't see the schematic?
No, I can't see you. Can you just go into Skype and check your video settings?
How about now?
There it is. Now I can see you. Thank you.
Oh, I hate technology. I swear to God, I did. I really wanted to be a lumberjack. You know, up in the great white north with the wind in my hair, jumping from tree to tree.
I'm a lumberjack and I'm okay.
And I'm
Oh,
okay.
not supposed to sing
Oh,
music on YouTube. But actually, I
yeah,
think that comes.
that's true. Yeah.
That comes
Though,
under fair use. That line.
though there is a great Monty Python skit about the wines of Australia. Have you ever seen that?
You have told me about this one before, and no, I didn't see it. And I did look it up after you mentioned it to me. Yes, and it was very funny.
So, hey, guys, we got a great show for you today. As it turns out, this is the 40-year anniversary of what? Of the Commodore 64 came out in
Wow.
1982. So we're going to talk about that. I have one here today. My only problem is for a moment I have lost the chat channel, so give me just a second here. And then we'll get started proper like.
That's okay. I'm monitoring chat on YouTube and Discord today, since Bill's going
Okay.
to probably end up doing most of the talking for today's show.
Right? We're
But,
almost there. Yeah, I closed the wrong window. Bad engineer. Here we go. Yes, hello, everybody. 40 years. Dead at work, so I'm able to stream. Hey, guys, Kevin
Yeah.
said, yes,
Hey,
we're
it's
good to go.
educational, right? You call it like it's work related. This is all work
Right.
related.
So, here's what we're talking about. This was the computer, in my humble opinion. Oh, first off, let's introduce ourselves. Ben, so I have a feeling this more people will see this than normally see our channel. So welcome to the Coriolis Effect with Ben Jordan, well-known engineer of all things high-speed engineering. I'm Bil Herd. I am a recovering Commodore engineer. I used to work there back in the 80s, and I'm still trying to get over it. So excuse me if I have tics and nervous itches and the desire to trash Apple from time to time. I've been known to do that. So my apologies in advance. I'm sure they're a good computer. Just ask them, you know.
Well,
but
they
I'm
were.
here to talk about Commodore.
They were at the beginning.
Well, Bill Mensch,
No offense, like
mother of the 6502, and he personally told me that's how he felt, the way he calls himself, which is funny because I call myself the mother of the 128. They asked him, what's your favorite 6502 computer? And he did say the Apple. And I do get that. The Apple was an open frame. It had cards you could slide in. It was educational. You could use it in scientific. Commodore was in a different
was
business.
Apple, Apple II, Apple IIe, Apple IIc,
Yes.
2GS,
Yeah.
3 were the antithesis of what a Mac is today. And I'm not knocking Macs. Some people love them, and that's quite okay. They're extremely well engineered hardware. Those engineers know what they're doing.
Right.
But what
Right.
was created was an open thing that anyone could add to, tinker with, mess about with. And the irony is Commodore was closed and became the one that everyone tinkered with, messed about with, and still does today. So
Right.
I don't know.
Right.
I think there's some irony in that.
Well, so I regard Commodore computers as toy computers. Yes, you heard that from me. We were a consumer product. We went to the Consumer Electronics Show, CES. That was our crowd base. Jack Tramiel is famous for saying we make computers for the masses, not the classes. And that's got to be a dig at, people like we're talking about. It was all about low price. This thing cost $299, then $199. And we had a special for a while. If you sent one of your other computers in, we'd knock $100 off. So what happened was people were out buying Timex Sinclairs, sending them to us still new in the box. So they'd spend $50. We'd knock $100 off the cost of a Commodore 64. It's made to be, it's got timing violations. It's got some quality issues. But we made between 12 and 27 million of these. We're in the Guinness Book of World Records for the most popular computer. And I don't know if we made 27 million. There's been some discussions lately where they've analyzed serial numbers and they think it's closer to 12 to 15. You know what? Still blows the competition away.
That's the whole thing. People, a lot of engineers I know, and myself included, we fall into the trap constantly because when you're designing something and you're trying to build it, we're engineers. We have a natural desire to build something that's really good, that's quality, that's reliable, that works well. It's kind of an innate aspect of being a designer and an engineer. And especially on the PCB side, the best PCB designers I've met in the industry, you would call them perfectionists, right?
Hey, check the feed, see if we're live.
No, we are. I did check it. It's all good. I was responding to chats on there too.
Okay, because I'm not. Okay, there it is. Wow, I really hate technology. Okay, I'm back with you.
But we fall into the trap of constantly feeling on.
Okay, we lost you there. Your audio, you're frozen. So there goes the disconnect. We are using Apple products here today. That's why we get these disconnects. Oh, sorry, I was blaming Apple for your disconnect. I'm still on cheap, crappy Cox Wi-Fi because AT&T still haven't installed fiber into my office. I'm waiting 3 months and counting now. 3.5 months and counting. So
anyway.
So you were saying,
like, we constantly feel like we have to go for a perfection, and then feature creep comes in because we keep getting ideas and we want to incorporate them. And yet doing something like the C64 is solid evidence of the fact is, as an engineer, your job is to be pragmatic, and that is engineering. That's right. The difference between engineering and marketing. An engineer, as engineers, we can bend and break the rules, but that's our job, is to know when we can do it.
Yeah, we have to obey the laws of physics, and marketing people don't.
And we also know margins, and we also know devices have margins. There's a voltage input low and a voltage input high, and a voltage output low and a voltage output high, and
propagation delays. Yeah,
the silicon is engineered to have margins with a smaller uncertain gap in the middle, right? And that's all of that is about the practicality of being an engineer. What it means is you can actually build a computer and you can violate timing or set up and hold here and there if you know what you're doing, and then you know that you're still using everything within its margins and you can get away with things, right?
Right. Now this one has horrible timing violations built into it, and we're going to see why today. We're going to look at the challenges they had. You can look at the schematic and see some of those challenges where they're just trying to get the clocks to work, and they're trying to get the DRAM timing to work, and that's what made the C128. We got the timings right in the 128. Well, I had the 64. Me and Dave Haney had the Commodore 64 to look at, so we knew where the problem. So we were able to be pragmatic and say, look, we're going to start with 0 DRAM timing issues. But when we look in here, we're going to see that production would do things like solder parts onto the board just to get it to pass the test jig. Well, that didn't mean it worked better. It just meant it passed the test jig. So, and that was life in the 80s. We were making this stuff up as we went along, the engineers that did this. So they
I'm sure
cleared a horrible
people
obstacle.
Viewing the stream right now are software developers. There's a lot of people who are into this are more on the programming side, right? And a lot of you have heard the phrase, oh, don't worry, we'll fix it in software. And
Yeah.
cringe. Because
Well,
a lot can be worked around with hardware limitations by doing clever software development. And 1982, that's when it really meant something to be a software developer. I lament the loss of that level of skill that people had writing those games, and the demo scene and what those people were capable of is all in assembly language, just amazing.
Right. So one of my stories along those lines that's in, by the way, I have a book out, Back into the Storm. It's about not the 64, but the time around TED and the +4 development and the 128.
Yeah. So
but
Bill,
one of the
when are you gonna do an audiobook version of it?
Somebody was saying that. Yeah. Yeah.
You got to do it.
That means I have to read the book. I haven't actually read the book. I only wrote me and Margaret wrote the book. Yeah. But one of the stories that I talk about in there is we got, at the beginning of the project, in this case, the 128, we got the IC developers together, the programmers together, and the hardware engineer. And we said, look, the programmers can ask for anything they want out of the IC designers, and they'll try their hardest to get it for you. They'll do magic, right? But in exchange for that, as we get closer to the deadline, we have to freeze the chip, and then so we can't make changes in the chip, which means bugs in the chip we have to live with. And then we get closer to the deadline, and bugs in the hardware we have to live with. So in exchange for having whatever they wanted, the programmers would have to fix all of our problems in software at the end of the day. And that was just the normal thing. As you say, a lot of people were programmers using this. I still, to this day, get people telling me how their career started either in IT or programming or whatnot, and it's because of Commodore. So again, 40-year anniversary of the Commodore 64. In my book, the most successful home computer, not personal computer, but home computer that was made. So somebody asked, who is my co-author? Margaret Morabito, who was from the old Run magazine, she was the co-author on this. She brought English to the table. I brought the stories. She brought the ability to actually make them into a book. So all props to Margaret. Couldn't have done it without her.
Yeah, so, she's a great co-author to have.
Yeah, yeah. So let's get started. Let's talk about what a home computer was back in the day. And first, I'm going to tell you about an amazing resource that's been there since the internet, almost. And that's Zimmers.net. There is a collection. If you go there, you'll see there's a collection of all the schematics, manuals, programs, all things Commodore are stored in an old archive-style fashion. It's not flashy, it's none of that, but it's a great collection. So most of what I'm showing you today, I got from Zimmers.net. So now this block diagram I got from 64 Wiki, something like that. You could do an image search for it. But what the Commodore 64 and home computers and small computers is basically a microprocessor, memory, and then input-output devices, right? And I've spoken with Chuck Peddle. I knew Chuck back before he passed away, who's the father of the 6502. He says, yeah, I did the O2, but what I really did was the I/O chips. And like, why is that so important? And he says, well, think about it. If you have a terminal, for example, it's no good that there's a processor there. It's no good that there's memory in there. You need I/O chips. You need something to read the keyboard, and you need something to make the display. So to him, it was about the chips.
Did he design the 6500 series VIA, the versatile interface adapter?
6522 VIA was designed by Bill Mensch.
Bill Mensch. So that chip is bloody brilliant. At the same time, the only equivalent chip sort of you could get on the Intel chipset side of things was the 8255. But the 8255 was lame. It was basically just I/O registers.
Right.
That's it. I/O registers. You couldn't configure bitwise operations. You always had to do read, modify, write. Well, we had to do that with the 6522 as well. But the 6522 also had timers, interrupts.
Counters. Yep, excuse me. Yep.
Timers, interrupts, and various other Well, I'll have to go back to the original data
No,
stream.
no, you're right.
It was a bloody useful chip. You could do so much more than this than an 8255.
And it enabled real-time operating systems, RTOSes. The one thing built into the 6522 that I appreciated the most I did instrumentation before I worked at Commodore. And I mentioned this to Bill Mensch, and he didn't remember doing it. But the 6522 has a self-reloading timer, which means we set a timer, we get an interrupt. The next interrupt will be in that exact clock, that exact time space.
It's ideal for real-time systems.
Right.
And that's
right.
And I had to do that actually in 1993, in my first 94 actually, second year of college. We had a microcomputer systems class, and we had a single board computer that we had to make using a 6502. We ended up using Rockwell 65C02s and 65C22 and the CIA as well, because we had RS-232 and did everything over the serial port. I'll break that out one of these shows because I still have it. But the 6522 was that was an
amazing chip.
Our assignment would not even be graded if we did not make it timing. If we didn't use the timer and make it interrupt driven, they wouldn't even mark our assignment.
And the reason why that's so important is if it's not self-reloading, it's up to the processor to get there as fast as it can and then reload the timer. Yeah. And you get jitter because it takes different amounts of time to get there depending on what it was doing in the process. So if you looked at the interrupts on a scope, they would do this instead of being like marching soldiers.
Yeah, you couldn't use it as an actual timer or a clock. You had to. That's why you have to have an auto reload counter for any kind of real-time application.
Right. Yeah. Somebody just asked about a 6502 versus the 80 comparison. Hey, we'll have to talk about that. We'll have to do this on a C128 where we have both, right? And we'll talk about that because they're comparable. They are, but the 02 is my favorite, but the Z80 is nothing to sneeze at. It could keep up with an 02 and vice versa. So now, remind me to talk about the 6526's bug that affected our serial port when we get to that.
Yeah. We'll come back to that.
So let's look at our block diagram here. Hopefully you can see my mouse moving around. Computers of the day had a microprocessor. Well, what's a microprocessor? It basically goes and gets an instruction and performs the operation and goes and gets another one. These operations consist of load, stores, and mathematical manipulations such as adding, ORing, exclusive ORing, all that stuff. But basically think of it picking something up, putting it down. That's what it does. Pick it up, modify it, put it down. So we need a processor for the intelligence of any processor-driven system. But there's certain things we have to surround the processor with to make it work, right? And so first off is we need a place for those memory for that operational code that it operates on. Now, I'll talk about reset circuits, clock circuits, power supplies, the things that I always look for as an engineer when I first look at a processor. But on this block diagram, you don't see the power supply. This is a logical block diagram. So we start with, we have ROMs in here. We had something called the kernel, which was the, I don't know, what BIOS, thank you. I was trying to think of BIOS of the day. And kernel is spelled funny thanks to a guy named Bob Russell. He spelled it the way it's spelled, and it's been spelled this way ever since. I don't think it's spelled like a corn kernel. Yes. He spelled it that way in a document, and we got stuck with it, according to Bob.
Yeah, I always wondered what...
So these ROMs were in... So again, the 64 was made in huge quantities. And so these ROMs, read-only memory, we made into custom silicon, right? But it didn't start that way.
Factory mask programmed?
That's right. That's right. It's an EEPROM that's not electrically erasable. It's preset at the factory. So the 64 would have started with EEPROMs while we're developing it. Those are those things that you can read and write multiple times. But by the time we go to sell millions, we can't afford EPROMs. Those things are like $1 a piece. $1 times 27 million is $27 million, you know, to give a scale to it. So the ROMs are, yeah, the one time I saved $1 on a transformer, I went and got very drunk that night. I mean, it was just, you know, that's how important cost savings were to us. So, but we have our ROMs here off to the side. We have the kernel ROM, which has all the input-output routines and the operating system. And later then, the kernel for the C64 was written by a guy named John Figgins. I believe he did the kernel, and he also did BASIC. I think it was pretty much him for both of those. The BASIC was an amazing version of BASIC at a time when you couldn't auto renumber. BASIC, you put a line number 10 and an instruction 20 and instruction, and then you insert between 10 and 20. Well, we came up with a version of BASIC that allowed you to renumber all those lines, and you could scroll up, change the line and hit enter, and it would enter it in a program. It's called a screen editor. This was an amazing invention. I fell in love with Commodore during my interview. I went to interview a Commodore, having not seen a Commodore till that day. And Bob Russell up arrowed, did something and hit enter, and I went, "Is that a screen editor?" And he's like, "Yeah, uh-huh." I'm like, "Oh, now I want to work here." You know? So it was an amazing ROM. Then we have the character generation ROM. This is a slightly different guy. These other ones are only read by the microprocessor, the kernel ROM and the basic ROM. That's the microprocessor going and getting stuff. Well, the character generator ROM is exactly what it sounds like. It generates the characters for the video screen. So that means that it's being read by the VIC chip. Well, we're going to see that we only have one address bus for all of these. See how they're all together here. And the VIC chip, where is the VIC chip in this guy? He's right here.
This needs some rudimentary DMA. This is where DMA comes from. And Z80 systems at the time and 8080 systems had a dedicated 8237 DMA chip. But the cleverness of the C64 was you didn't need, because of the way the VIC chip was designed, it had its own DMA. It could halt the processor, right? Processor would let go of the bus so that the video, which is critically important, could real time pull characters or bitmaps out of DRAM and go straight to video. That was,
and it wasn't its only trick.
Source.
It was an add-on, but and we're going to go around the horn here and end up on the VIC chip. VIC chip means video interface chip, by the way. So when you hear Ben and I talking about the VIC chip, we're talking about the video chip itself, almost as famous as the 64, in my humble opinion. So yeah, so we end up with this address bus that we end up sharing. And so I'll stop and explain that right now then, since we're talking about DMA. On every single cycle in the normal address bus, we have this window of time the processor normally gets its chance to get to the ROM or get to memory. But then the VIC chip has a crack at it, and then the processor, and then the VIC chip. So they spend their time doing this. And that is like the thing that that opened up the door to real-time graphics. Prior to that, you had to wait for the time called the retrace times, when the dots being made across your television, and then there's this time where the beam comes back, you could read and write to memory. Well, that's no good. You can't wait to write to memory. You need to write to memory right now. So by doing the sharing where we're doing this, we could read and write to memory. The VIC chip could read whatever it wants, and the 6502 could read and write whenever it wanted. And then, as Ben mentioned, the VIC chip was very smart, and there was times when he said, "You know what? I need even more bandwidth. You stop moving," and that would be the 6502, and it's called a DMA, direct memory access. The VIC chip would say, "I'm taking over both these cycles. I get 1 and 2 and 1 and 2," and he would do these things called sprite pointer fetches, and we'll talk more about that. So,
hey, there's some questions coming through the chat, Bill. Just going back to the screen editor real quick, Kurt's asking, did the PET do that as well? It's the same people, so maybe. I don't know. If somebody could tell us whether PET had the same.
So I didn't see a PEP my first day there. I do have one in the background here, but I haven't really tried to get it working or anything.
Yeah,
But
and someone else,
it's same
Arnold
crew.
was asking about why, by default, the text was always uppercase only.
So let's talk about the text. Hang on. You know, I was looking for my VIC-20 and I don't see it, so I'm not going to waste time on it. Inside this character ROM, which is how the letters actually get made, what happens is you tell the VIC chip, and again, we'll get to the VIC chip in a second, but you leave in memory a value that says, hey, make the letter A, hey, make the letter C or something, and we store it as
it's
two
a pointer. So it's
it's a
you have
pointer.
an array. If you have 8 bits, you could say a character could be 8 pixels high, because that gives you 5 for the actual character, or 6, and a space line, and a 7th for underscores or other things, or commas, which go below the line.
Descenders. Yes, those things that...
You have a base address, and then it's an array of however wide your characters are. This is where fixed width fonts come from, right? So you might have a 5-column character width, and so it's just a big array of bitmaps, and you're pointing at the base of each character.
That's
and
right.
You can even do that by, well, anyway, I'll let you go, Bill. You go ahead.
No, you're absolutely right. It's a pointer to, instead of 1 byte points to 8 bytes in an 8x8 cell, right? So there's the top row, the next row, the row. So the VIC chip tracks which row you're on. So when it says, oh, there's that 20 again for that character, but now I'm on the 3rd row, so it goes to the character ROM, and it gets what the 3rd row of dots looks like to make the letter A, for example. So it's a pointer to even more bytes in memory that are rows, and then the columns are the character columns.
Yeah.
So now, the source of our character ROM in the Commodore 64 is, wait for it, we stole it from Atari. We used to do, we were the biggest mask ROM makers in the States, is my memory. We had big posters in the hallway. It says, you want your ROMs by Christmas, and it showed a picture of Santa Claus with a bag full of Atari ROMs. So Atari wasn't our competitor, they were our customer back in the day.
I love it.
And to thank them for it, we stole their font ROM, right?
I know.
And there's
6502s and all of that as well. So they were MOS customers. They were business partners, let's say.
Yeah. Oh yeah, I had the most respect for Atari. I think I even have an Atari T-shirt around somewhere. And I started on my first video game I ever played was Pong. We used to walk to Sears in downtown Marion, Indiana, and go in the basement of Sears down near where the return center is. And there was a Pong game. We'd walk in there with pockets full of quarters. And then later the 2600 came out, and so I'm from that era. You know, I grew up on an Atari 2600, quite literally. So, and we'll find when we talk about the 128, when I tried to be Commodore 64 compatible in the 128, we moved the dot in the I in the font ROM, and we actually screwed up compatibility. So the font ROM is part of the operating system, even though you don't think of it that way. And that's because programs are free to read those characters and make them larger and bigger and memory map them and whatnot. And there's stories about that. So coming right below there, though, is our dynamic RAM. And this dynamic RAM in 64K by 1 was the magic juice that made all of this possible. Up until this time, we had the VIC-20, and I think it used 4K or 16K static RAMs is my memory. Dynamic RAM, DRAMs, which are right here on the diagram, they were these tricky, noisy, hard-to-use devices, right? Normally, if you went to build a DRAM controller yourself out of hardware, Ben, if you and me were to try it without a VIC chip, we'd have handfuls of either programmable parts or just handfuls of support chips. Yeah. We'd have to create our own refresh. Dynamic RAM is exactly that. It's dynamic.
We would have probably, I'd guess, up to as many as 6 additional 7.4 series logic devices on board. We'd have 8-bit refresh counters, which run separately and have to get access to the address bus and the RAS lines within the appropriate refresh period. You'd have to have multiplexers to give access to the refresh counter and prevent other chips trying to access.
You have to stop everybody while you do the refresh, yeah, which is a form of direct memory access. Yeah.
And you'd have to have additional logic around that to try and optimize the system so that you're not refreshing something that's only just been written to.
Right. So a trick was a trick was the day is you could use the fact that you're writing to a video stream to refresh your DRAMs, but that only worked for the rows and columns that the video RAM, it was accessing. So I before I worked at Commodore, I had bought a tube of 64 K DRAMs because they were the chip, right? I bought Motorola 6665s, which had auto refreshes built in them, so they were more expensive. Commodore's not going to pay more for anything, but that's how me as a lay engineer was going to deal with refreshes. On my own circuit. It
is still a thing today. This is why you can buy PS RAMs, pseudo SRAMs from Mauser, DigiKey, whatever, and they're really fast, and you read and write to them with an asynchronous SRAM interface. But under the package encapsulation, it's actually a bunch of DRAM with its own control circuitry that takes care of refresh and does everything for you, and you don't even have to think about it. But they're horrendously expensive. They're almost as expensive as SRAM, at like about 4 times the price of DRAM. So if you can put up with setting up DRAM and configuring, even modern DRAM, it'll do the refreshing for you, but you have to go through an initialization sequence. So it's kind of a hassle.
Hey, they're talking about the AEC line in the chat group. I can barely see it without my glasses on, but I want to talk about AEC when the time comes, Joanne. So so continuing around the horn here, because I want to get to the schematics. Here's the bottom right is a 6526. This is an I/O chip, input output. It's got the address bus and data bus go in one side, and out the other side come just lots of ports. And we can take these ports and put them together in a matrix and make a keyboard out of it. Matter of fact, there you go. There's the input-output lines coming in and out of the 6526. There's a ferrite bead to try and reduce the noise on these. We love these things. This is here to make us pass FCC emissions better. Even the LED has one on there. You can see it's a little toroid.
Of course, no one knew.
But these are the I/O lines.
No one knew how to do that cheaply back then. Ferrite beads are actually horrendously expensive and a terrible band-aid. If you were doing it again now, you'd have a 2-layer board with a plain layer, and you'd have a flexible printed circuit that had lots of grounding on it to keep your fields constrained to the flexible circuit. But back in those days, things were slower, and on the hardware design side, we didn't know as much. We knew about EMI and had to meet requirements, but it was a bit different.
So we had a disk drive at Commodore that failed FCC. I think it was the 4040, and we were being fined something like $10,000 a day for every day we made the disk drive. And we kept making the disk drive because somebody did the math. This is what I heard. Somebody did the math and figured out it was cheaper just to keep making the disk drive than to try and rev it. Yeah. Yeah. So we are not innocent people, us at Commodore. I'll tell you right off the bat.
What other industries does that remind you of, Bill?
So coming around the horn here, we'll talk about voltages. That's actually where we'll start on the schematics when we get there. Here's our second input-output CIA. Oh, I've forgotten what CIA means. Guys in the chat room, somebody look up CIA for me.
Communications interface adapter, right?
Thank you. I did not know what that meant. We just called it the CIA.
It's not this agency, because that would be the processor if it were.
Right. So so those drive the user port and the, what's the other name of the port? The serial port, which is where our disk drives were. So these ports here are, I'm actually touching with my fingers, so I shouldn't be doing that. and the serial port. So one I/O chip is used to read the keyboard, the top of it. The other I/O chip is basically used to read the back of the 6502.
That's a great question. So that's something else I want to come back to when we come to the schematic. You don't have to answer it now, but you mentioned touching the ports. Those were card edge connectors, and
right.
Like how you guys mitigated static damage is something
we didn't
we look at as well.
Yeah, we basically didn't. Other than the chip had standard crowbars in them made out of JFETs on the pads themselves, going in the chip, which tried to act like a diode to take any voltage over 5 volts and ground, connect it to the 5 volts.
Also relying on
it's
the intrinsic
naked
body diodes of the part.
That's right. That's why it's a JFET. Was you get you make a JFET look like a diode, and that's part of the process of making the pad. Was you had the parts of a JFET laying around.
Okay.
So, so continuing up. Oh, the next one here on the left is the SID chip. Yeah, sound interface device, made by a guy named Bob Yanis. Was the genius behind that. Bob was also a musician, and it shows. So if you like the sound of the 64 and the voltage controlled oscillators, voltage controlled filters, white noise source, all those things, that's Bob Yanis. And that was a part that had more than 5 volts going to it. This is an NMOS part that's got analog on it. It is like baking a cake. Right, it's almost as famous as the VIC chip. Depending on your circles, musicians probably more so.
Famous than the VIC chip.
Yeah. So we're going to then talk about the clock generator circuit, and we're going to find out that the early 64s, this was a big part of the limitations of the 64, was generating the high frequencies and the timing constraints we needed to create all these windows in time and everything. Finally, we get to the VIC chip itself, and you'll see it says here, NTSC and PAL. NTSC, National Television Standards Committee, PAL, phase alternating line. This is basically the American and the European versions of the television standards, even though PAL got used other places as well as NTSC. So we made 2 versions of the chip. Later, when we did things like the +4, we made this, did we? I thought we made the same part do both, but now I don't trust my memory. And hanging off of there was just a little bit more RAM for color information. So this is an 8-bit machine, except for we've got, and what we did was we address mapped it somewhere else. We had this little nibble, a nibble being 4 bits, of color information. Well, you make 16 colors with 4 bits. So this is why a Commodore 64 is a 16-color machine, is the width of the color. Now, I've had people ask me on the 128, oh, why didn't you make it 256 colors? I didn't have the pins. I didn't have the band. I didn't have the plumbing to add 4 more bits to anything. And we'll talk about that more in the 128 if we want to. This was kind of, this put the chipset to its limit. We ran out of pins after we added the color SRAM.
That must be so satisfying to design something where you use every pin, though.
Every pin, yeah.
Yep.
So going to
these days. Oh, that's kind of fuzzy on my. Oh, that's better.
It is, and I apologize for the fuzziness of it here.
That's not bad. That's actually not too bad. And those schematics were hand drafted back then.
This is hand drawn.
This looks beautiful. I don't know who the drafts person was who did these, but they did an amazing job.
So this drafts person was Ida-san from the Tokyo office. Sue did the American ones, and actually when we look at some of these where they leave the title blocks on, if you can read the title blocks, I'll tell you who those names are, as long as I can recognize the, because this isn't the best quality. It's 40 years later. Go figure. So this is off of Zimmers.net, so you're welcome to follow along. Let me find the power supply stuff first. All right. Here we go. So here's the power connector coming in. And I do recognize that this is a little hard to read, but there is something hidden in here. This is the DIN connector down here, and we bring in 5 volts from the power supply. This power supply has a bad reputation, and I'm not going to say anything to make it have a better reputation. This thing was nothing more than a heat generator. It had poor load regulation, which means as you add more load to it, plug in more cartridges, the voltage drops. Well, you know what? That's actually good, because somebody came along with a CPM cartridge that took 1.5 amps, well, this is only 1.5 amp supply to begin with. Yeah. So that was a reason. And so what happened then on
5 volts was only that 5 volts is only 5 watts. It's nothing.
Yeah. Yep. So look at what they did here. Here's the 9-volt AC coming in, and somebody ran it to a regulator, and then they ran it to a second 7805 voltage regulator.
The CR4 is a rectifier bridge. Is it a 1 amp bridge or a 3 amp bridge? Well, I guess it's a 1 amp bridge because you've got a 1 amp fuse on that line.
Right. So we would have over-designed the rectifier, and it probably, it's same thing. We probably tried to draw more out of it. But this was a change. I can tell, from my memory and from working there, somebody went in there and they did this as a fix. They said, we're burning up the power supplies, but we can take the 9 volts and we can make a second 5-volt supply inside the Commodore 64, and we called it the CAN plus 5. So
why are there 2 separate 5-volt supplies?
Well, that's why, because we used as much current out of one as we could, and then we had to steal more current from the other supply. Now, this had the benefit, too, that we ended up with 2 separate 5-volt supplies. The CAN volt, what we call the CAN, which was inside the shield, it did the VIC chip. And so we wanted a slightly quieter supply. And I used to think this is why there were 2 supplies. We had a supply for the video and a supply for the processor. And the idea was that the noise from one wouldn't get as drastically into the other. I don't know if that's true these days. It might have been just due to current draw. And I'll show you why on the cost reduce.
Did it damage either of the chips if the 1 amp fuse blew but the other 5-volt supply stayed active?
Not that I know of. I want to say that there was no 1 amp fuse. I don't think we fused. Yeah, there's a 9 amp fuse on the 9 volt. Right, there is a fuse on the 9 volt, but not on the main 5 volt.
And the 12 for RS-232 or whatever, or the VIC chip had a 12 volt. So, but if one failed but the other didn't, would that cause damage to any of the devices?
Great question, and I've seen that fuse blow, and I'll tell you that in NMOS parts and CMOS parts, it can turn any pin into a power supply. So while it's not recommended, the VIC chip would try and at least power up from its own address lines and data lines. So we're abusing the part. It's non-ideal, but my memory is you could replace that fuse and have it still work. Guys, if you're into fixing these things these days, tell me if I'm wrong. Go ahead and post it to the chat channel, and I'll gladly say, well, I learned something then. But that's a great question, and on the 128, it wouldn't boot without 9 volts, but that's for a different reason, dealing with the Z80. It just plain wouldn't boot.
Yeah.
So here's our supply, real rudimentary, real heatish, makes a lot of heat, right? Right above it to the right here is our reset circuit. And it's a 555, but there's no reset button. That meant you had to power cycle the Commodore 64 to reset it. And I'll tell you, the Commodore 64s did lock up due to some timing issues, and we'll talk about those timing issues.
So that's the #1 mod, is to add a push button that shorts out C105, so you can have your own reset button.
That's right. And we'll see in the cost reduce, Katayama-san tried to get rid of did get rid of the circuit. I'm not sure. I will have to look at it and judge it on its own. Now, somebody posted to our Discord. By the way, our Discord's available at Coriolis-effect.com. If you go there, there's a Discord invite. Yep.
Join the Discord.
And
we have quiet days on the Discord, and then other days that very, very active with really interesting discussions from the group and projects people are working on and photos of what they're doing to their own retro computing devices and other things. So join us.
Now, somebody just said they didn't know there was a 555 reset circuit. I want to be clear. This is the earliest Commodore 64 schematic I could find on Zimmers. This is what was there when I first started. So I'm going to show you a more advanced schematic where they got rid of the 555. I shouldn't say advanced, but more cost reduced. Let's call it that. So this is our reset circuit. And then somebody posted to Discord where they showed that somebody tried to get rid of this open collector buffer. Made a mistake. You're allowed to ground the reset from this back connector on the back of it, and it would short out the 555. So somebody in the Tokyo office thought, oh, I can get rid of that. And they missed the fact that it's supposed to be an open collector, which means it's a party line. It means other devices can pull it low. You can't pull it high, but wired or, right.
Wired or.
So now here's the poof. This is what made the Commodore 64 in 1982 hard to make, and it was the clocks. We needed 14.3181818 megahertz for NTSC, and we needed a dot clock at 8.181818 megahertz for the dots on the screen. 14.318 ran the chroma, the color demodulation. It's what the TV set expected to see. But the dot clock was used to derive the microprocessor frequency. If you divide 8.181818 by 8, you get 1.02 megahertz. That's the clock of the microprocessor. I think originally, and the way they make these signals is they use a 74LS193. I think I have one here.
That's a counter. Yeah, it's an 8-bit loadable or 4-bit
actually the
counter.
Right, the 193. Yeah, I pointed to the wrong part. They whoops, excuse me everybody while I reset. I'm sorry, they used this 74LS629 right here.
That's we can't see that.
You can't see that. Let me reframe that real quick for you. So let me delete this and add source, screen capture, smart capture. And I apologize that there's not better schematics. By the way, there were schematics in the actual programmer's reference guide. Picture that. You buy a computer for at home and there's the schematics for the whole dang thing built right in it.
That's better. Now I can see the that
LS629.
There's a whole like 2 inches of that was cut off. And then,
right.
like I couldn't see the voltage regulators before.
Okay. Oh, excellent. There's the voltage regulators.
Yeah. So I wondered what was going on.
I apologize. Yeah, scream when I do that. And it won't be the last time I'm pointing to something you can't see here today.
The 629 is a PLL or
it's a voltage controlled oscillator.
A VCO.
So there is a PLL. It's right here, and we're going to see why it's there. But originally, it was 2 voltage controlled oscillators. This one here, I can't make it bigger.
It is crystal
easily.
It is crystal locked.
Use a crystal. But look, there's a resistor here too. There's an adjustment resistor right here. So we used to be able to trim it for you'd get running rainbows on the screen, or it would lock up in a good sense, and you get your colors locked in and see your nice red, blue, and greens. Right.
Yep.
So originally the 64 started with a voltage-controlled oscillator for the 14 megahertz with an adjustment. And then there was this 8 megahertz, which was just an RC base. Well, one time I heard that the first problems they had with the 64 was video noise and some other timing issues. And there was moving noise. Well, if your dot clock is completely asynchronous to your 14 megahertz clock, you're going to get moving patterns.
Yeah.
Right? Moiré patterns. So somebody did this. This is a work of art. They put in a phase lock loop and they created this frequency control voltage coming out of this phase lock loop, which said, however the 8.18 oscillator got to where it is, we want it to either increase in frequency or decrease in frequency so that it's stable, locked. It's frequency locked at some ratio between the 14 megahertz and the 8 megahertz.
Yep.
And this is a lot of circuitry.
The the ratio comes out of your 193 there. So that counter is used to divide
That's right.
down. That divides down to 14.31818.
Right.
And that's your input. That's your input to the PLL. And then there's the phase detector, charge pump,
Right.
the VC, that transistor, and the Schmidt trigger IC or whatever it is there.
That is, yeah.
That's your control voltage output of the phase detector into your VCO, which is another LS629 underneath,
Right.
and the output of which is your multiple of that, or phase locked. And these are used. This is all done now in silicon. You go get an ARM microcontroller. It's got its own PLL, and it does all of this internally, and you can program it. Or you get an FPGA. You get a Xilinx FPGA. You can do it with a delay lock loop, they call it. It's done purely digital. But yeah.
So look what we did here then in the later version of it, of the Commodore 64, is we replaced all of that with a single chip, just like you're talking about. Hey, we make custom ICs, right? So in the cost-reduced version, which was done by an engineer named Katayama, he specified an 8701, which has all the phase lock loop circuitry built into it. So right here we have, we're just on the edge. I realize you can barely see it. Here's a crystal.
Yep.
And this generates the 14.318, and it generates the 8.18 megahertz, both for the VIC chip. So you can see that on this newer one I have. It used to be, all of this area was clock generation circuitry. This used to be a whole big can around here. You can see this. And now it's done with just a VIC chip, an 8701, and a crystal. So this is a later model 64. You can tell by its clock circuit.
Yeah.
So, but the guys that did that first one, they're making that up as they go along. They're like, oh my gosh, how are we going to make, and being good engineers. And this is the Tokyo office in Japan that did this. They came up with the phase lock loop circuit to make it work. So let me try and get back to a schematic we can look at together. Which one? All right. So let's start.
So we've done power supply, we've done clock.
And we've done the reset circuit. And I'm trying to find...
And we're 7 minutes to the hour.
We're going to run way over today. Okay, so let me get this one expanded here, see if I can make it easier to read. It's not working for me. Smart selection. So I was just going to go, the original C64 schematic is 2 pages, and then on the cost reduce, it became 1 page. So if we look at the processor side, so here we are.
Yep.
Here's our serial bus. The serial bus connects to one of the CIAs, and it was how we did the disk drive. I wish we did it perfectly the first time. We did not. So if Apple did beat us to the floppy drive. Our cassette controller works so well that Chuck Peddle wanted to keep the cassette deck and would argue with Jack Tramiel, or so I've been told, about whether to do a floppy controller. Meanwhile, Apple really did come out with the floppy drive before we did, and they beat us to that punch. So we had this serial bus for our drive component. Oh, do I have a drive here? I don't have a 1541. Back then, our drive was called the 1541, and it cost as much as a C64. So here we're getting you computers for the masses, but then it cost twice as much to get a drive. So people were using their cassette decks, unfortunately, and actually hand typing in. It's the 1980s. They get a magazine like Run Magazine, and they would hand type in all those commands to see a basic game run. Well, think about it. You can make a game in BASIC. What a wonderful time to live. I mean, you could do one in assembler if you wanted to, but you could do it in BASIC. So these, we have here the control ports. Control ports. These are the ubiquitous, what we call the Atari. By the way, they're Atari compatible. Yes, we swiped the Atari joysticks, would plug right into here. I don't even know if we got sued for that one, but they work. My favorite joystick was a third-party joystick made for the Atari. So these are I/O ports going into there. Here's our processor. Let's see if I can zoom in. Care and feeding of your microprocessor. And unfortunately, I don't have... Oh, there's a mid-step. This is a takeoff on the famous 6502 processor. We owned MOS, who was the founders of the 6502. It was later made by Centertech in Rockwell, but we couldn't leave it alone. We had to open it up and add things. So we opened it up and added a port on zero page, and we used it to generate memory map helpers, low RAM, high RAM. These would run to the programmable logic that told the memory map how to work. And I'll show you that programmable logic here in a bit.
Because you have a von Neumann architecture CPU with one memory space of 64 kilobytes. And yet here we are, you've got 64 kilobytes of RAM, 16K of kernel and basic, and another 4 characters.
Yeah, you're breaking up.
How do you map
okay,
all
you're
that
back.
when you only have a 64 memory space? Yeah.
Right. So we even had a mode in the Commodore 64 where we had, guess what, all 64K except for like that page 0 RAM. The Apple, I believe, could only go up to 48K of its 64K. I don't think you can ever get all 64K out of it.
That meant that they didn't fit the chips on the board, right? There's no point adding them if you can't access them.
Well, they had a 64K by 1 architecture also. It's just part of the memory when unused.
Unusable memory, which is really, that irritates me.
So the thing that irritated me about the Apple... yeah. The thing that irritated me about the Apple memory map was they did something called window painting, and that is, in the 64, the memory map is contiguous from the start. You just, as you increment, you're moving down the screen. They would do this, if you've ever seen Apples do this thing that looked like Venetian blinds called window painting. That was due to the way the memory map, if you wrote straight to memory, you'd write to this row, then this row, then this row, and then come back and write to the second row, something like that. Don't quote me on it, but we had a linear memory map, and it was window paned in there. So some other signals that are on here, look, so we have the non-maskable interrupt, which we run to the break key on the main keyboard. Interrupt request. This is any timer that times out, basically timers that time out, use the IRQ, interrupt request line at signal slow. It's a party line. Anybody else can pull that interrupt line low. Ready goes along. Let's see if I can see. I can't show you the ready logic yet, but ready is part of how the VIC chip tells the 6502, I'm going to do a DMA. I'm going to take over the bus. So here's our clock in, phi 0, phi 2 is our clock out. Somebody threw a ferrite bead on here because, hey, it's Commodore and it's the 1980s and we have all that we can do to pass FCC. Up in the top right,
relationship of phi 0, phi 1, and phi 2?
Phi 1 is 180 degrees out of phase and was not used. It sounded like a good idea when they made the 6502. Phi 2 is delayed by about 10 nanoseconds off Phi 0.
Yeah,
so a trick you can do,
phase shift, it's a fixed time.
Just a delay in one case, yeah. So a way you can see the future is to use Phi 0 instead of Phi 2. If you need a gate off Phi 2, but you don't have enough time for a full logic delay, we would use Phi 0 because it comes out 10 nanoseconds earlier. So it's like seeing the future. It was pretty cool. So up here we see the cassette. I won't talk about it much because we are already to an hour. But this is how we ran the cassette motor. We could turn it on and off externally. So there's some circuitry to do that. All right, I'm going to jump around a little bit. I'm going to go down the... So here is... Where's my address enable control? Here is the signal. Oh, let me... sorry, I need to Let me... So here is an entire page schematic. So I'm going to jump to it real quick just so we have a good page to talk about.
Full screen on it. If you
yeah, this one I can do full screen. I apologize that the other Zimmers things weren't but let's talk about here we're talking about AEC and which means address enable control. This is the thing that tri-states or tells the microprocessor get on the bus or get off the bus. And here we see we take a DMA, which generally comes from, I want to say its source is down here in the corner. This is so external cartridges can do DMA. So in addition to the VIC chip doing DMA, external cartridges can do DMA. And so we end up creating a combined AEC line here. Well, this AEC is also controls how we talk to the DRAMs, and here's our DRAM array. 64K by 1K of DRAMs. Too fast and they don't work. Too slow and they don't work. We had a dickens of a time getting these DRAMs to work, and one of the reasons is we didn't have enough clock edges to... Here, I'm going to make it so you can see me while I talk here a little bit. There is this signal. A DRAM works by first giving it row addresses, and a clock strobe called RAS, row address strobe, drops this RAS signal. It's this Viking-like signal. It says, "Aha! I've latched the row addresses," right? And then we have another signal called CAS, and he latches the column addresses. What this means is, for 16 addresses, we actually multiplex them onto an 8-bit line. So this is an 8-bit address bus right here. And at first row, first column, this is pounding its ass off. This thing is going row, column, row, column, row, column for the processor, row, column for the VIC chip. And it's driving all the capacitance of this DRAM array. This thing is humping. This is the hardest working signals in the entire Commodore 64 are these multiplexed address lines. Well, guess what? We didn't have impedance control. We couldn't afford 4-layer boards. I never even saw a 4-layer board till years later, right? So we had to put in these series termination resistors, and my memory is they're 33 ohm resistors to terminate this. And basically what happens is reflections do occur as this signal drives this array and then bounces back, and it gets absorbed by these multiplexed address, by these termination resistors. The problem with the control of row and let me get the mouse here. The signal that selects whether you want, see that says select A right here, is a signal called CAS. We're using the CAS signal to determine, to make the row and column addresses switch. That doesn't work. Okay. Here's the row address strobe, fine. But then here's the column address strobe. Well, he not only strobes the DRAMs, he also selects the memory to the DRAMs. Well, CAS actually goes through the programmable logic down here in the corner. Let me see if I can show you. So we're relying, so CAS comes in right here to the programmable logic. We did have a chunk of commercially available programmable logic called the 82S100. Later, we made our own PLA for it. And CAS would come in and CAS would come out and be called CAS RAM. Well, that meant that the minimum delay through that part was critical. Well, wait a minute. You just told me having a fast part is bad, right? If the part is too fast, and we always want our parts to be faster, we'll screw up it's called the row column address setup. So we have this CAS signal falls, and then it switches the column addresses, and then here's CAS RAM falls. In production, they were putting capacitors on here to try and stretch it out. They were doing all these tricks. And this is the heart of the Commodore 64 timing issues, is we did not have a signal that said RAS. Okay, switch your multiplexers, CAS. We had RAS and CAS, and we tried to make CAS not only switch it, but we delayed it and then sent it to the DRAMs. It's a race condition, it's called, racing condition. They're too fast and it didn't work. If the DRAMs are too fast, they didn't work. So we couldn't use 120 nanosecond DRAMs. We could use 150s, which didn't exist when I first got there. Yeah, we used strictly 200s and then migrated in the 150s. So,
right, but the point is you're using some propagation delay plus a few other analog tricks to delay the CAS.
That's right. So I'm going to speed up here as we go because we really are out kind of past the time. Here's our color RAM. This is that nibble, and we got to talking about this the other day. This is where I got the idea to do this show today. Was we were talking about the color RAM. We were talking about this 4066. Ben was talking about it. Yep.
One of my favorite parts.
It is. It's a wonderful part. And what this did was this allowed 4 bits. You see data 1, 2, 3, and 4 right here. It's hard to read, but that became the 4 bits of the color RAM on the early versions. And this 4066 was wonderful in that we didn't have to tell it what direction. We would just have the 4066 turn on, and then whether we read through it or write through it, the 4066 was a bidirectional valve that just let it through. So on later versions, let's see if I can show you a later version. I thought I had this queued up. I apologized. It's... Look what... Yep,
down,
look what's...
You scrolled down.
Yeah, I'm going to... Let me try and find a zoom that works here. Let me recast this one. And I apologize to everybody, but there was no other way I could figure out how to deal with all these different sizes of source other than on the fly. So what happened in the later version of the Commodore 64, again, the engineer named Katayama was in charge of the cost reduce era. And so at the same time, I'm working on the 128, and he's helping me with the 128. He's my liaison to Tokyo. I'm his liaison to Westchester, which it was where we were doing this work, Westchester, Pennsylvania. And he has this gate array in here. You can see it right here. And what they did was they built the color ROM directly in here. You see D1 through D4 right here. It goes into the... So not only did he combine the chip select logic, he combined the color RAM, he combined the IO select, all this stuff. You can see XROM, game, ROM high, ROM low. All that got sucked into a chip. And again, this board got easier. This one still has an A2S100, but we were able to cut the size of this board down to about here. So it went from about here to here in the cost reduced versions. Why is that important? Well, when you're making $1 million of something, the cost difference between here and here might be $1. And again, there's millions of dollars, tens of millions of dollars just in saving. The other thing we did...
That's product lifecycle management, Bill.
Yep.
Engineering is a critical component of PLM because you have prototype, you have early production release, and then the product life cycle goes over this curve where you get to adoption, you get to mass market, you have to do cost reduction.
Right. And so you hope that your cost reduction engineers understand true engineering and margins, because their job's to go in and make everything as cheap as possible, right?
And there's a double benefit. A lot of companies are only thinking about cost reduction, but actually if you do cost reduction properly, you're also reducing your environmental impacts quite significantly.
Right. One way we did a cost reduction, you'll get a kick out of this, Ben. When I started, around that era, we were still tinning the PC boards underneath the solder mask. All right? Well, guess what? we're losing 1/10 of an ounce of solder per board. That adds up.
It
So
does.
another way we save money is we stop tinning the boards. What's that mean? It means that we have copper and just solder mask on copper now, whereas before we'd take copper, run it through a solder machine basically to coat it with solder, and then put our solder mask on
level
it.
before your solder mask goes on, and we would.
Yep.
You would never even think about doing such a thing these days.
Right. But back then, we're making this stuff up. We're inventing how to make millions of a consumer computer. And again,
back then, who was the board house? Did you have your own fab in-house for the boards as well as semiconductors, or
it was in Japan. Kentron, Kentron. It's Kehtron. I've been there. They're up in the mountains. I forget the city they're nearby, but they had it made locally, and then they would do the stuffing. And the Tokyo office, there's guys that almost lived there. So we were in a real tight loop, just as you said, product engineering. The Japan office made it possible to make 27 million of these things by virtue that they were riding the production cycle over there. We'd get to the United States, they'd get shipped to the United States in components, like you'd get this as one component and then this as another component, and we would do that and then put them together in the Bahamas, things like that, so that we weren't importing computers. Yeah, we're importing computer components, not computers.
Exactly.
So we did final assembly in Westchester later on. Yeah.
Your phone and your MacBook's final assembly is always in Cupertino because it prevents excessive import duties.
Right. So we're coming up to the end here. Let me zoom in a little bit on the SID chip here. Oh, and we'll show the modulator. So excuse me while I do it one more time here.
Now the joysticks had analog. That's what your pot X and pot Y signals go to the SID, because it also did this A to D conversion for the joystick positioning. Right.
And I forget what kind of AD conversion it did. It just basically charged the cap. What's that version where you charge the cap and check your recharge discharge times is how. Yeah. So the audio the audio coming out of the SID chip goes into an emitter follower just to buffer it, and I do the same thing on the 128. So here's our buffered audio out, and then we send it to the modulator. What's a modulator? Well, back in the 1980s, we used TV sets. We didn't have home monitors. We had TV sets. You walk down the halls of Commodore, you look in offices, you see TV sets everywhere. You hear boops and beeps and all this stuff going on of people either working or playing games. You couldn't tell. And it was the kind of environment where if you were playing games and not getting your work done, you didn't last long. So you were allowed to play games, right? Because you were trusted to get your job done. You got to test the product, you got to develop the product, and you were trusted to get the job done, quite simply. And unless you were a manager. Different topic. So what we did, though, is we took the luminance, the black and white information. We took color. Whoops, you're not seeing my, there we go. We take luminance out and color, and we put them into the modulator, and I actually have a modulator schematic. The modulator, it's going to make me redo that one too, isn't it? Son of a gun. Well, let's go back to that. Let's show the modulator.
Screen on that one, because that's where some analog magic happens.
Yeah, I'm going to. So the one part of the 64, and this was true in the 128, it was true in the plus 4. Matter of fact, I'll do the whole schematic, whole thing. Was we used a pre-can modulator. I believe it was made by Mitsumi, one of our partners in Japan. We were not allowed to touch this thing. This thing's pre-qualified to connect to a TV set. So we have FCC to make sure we don't emit radiation. That's one form of FCC. But the other one is, whoa, wait a minute, you just hooked to the antenna terminals on a TV. New game, you have to have a different kind of qualification to do that, and this modulator was qualified to do that. This modulator.
We use off-the-shelf microcontroller modules that are pre-FCC certified for Wi-Fi.
Right,
too.
Bluetooth, things like
Same
that.
deal.
Yes. Yep. You use their FCC number on your final assembly.
It doesn't have to be certified though. It doesn't
Right.
mean that. You still have to go through EMI and all those hoops. But
Right.
it does reduce the effort.
So one of the things we did with the modulator, though, is we had color and luminance. Is we used the modulator, and this is where Mitsumi helped us out. They made this mixer where we have composite. You can see it right here, comp out. So we don't not only have RF out, which is channels 3 or 4, and that's where, if you've seen the old switches, that where you select a Pong game or your old antenna, and I grew up with a rotor and an antenna. You had that selector switch, which was part of the whole verification process. There's something like 60 or 80 dB of isolation. That's why it switches so big, is it isolates this channel 3 so that you don't transmit channel 3 to your neighbors. Because in effect, this becomes a TV transmitter at this point. So It's a low power TV. But one of the things we did was we said, well, monitors, we are making the 1701 now. We are making these 1702 monitors. We had the modulator create our composite output for us. And also, my memory is it amplified. This looks like an emitter follower. But my memory is it amplified the color output, or at least cleaned it up, peaked it. Let's say it peaked it, so that we could do a full 1 volt color signal to the monitor. That put us heads and tails above everybody else, because the composite, the color is only at 0.15 to 0.3 volts in height. Here's 1 volt of color. Well, guess what? There's less noise in 1 volt of color. So this was part of the Commodore magic, was making this. And you know what? It's an early version of SVHS or whatever that.
That's right. Yeah. This video, they separated them. It was probably inspired by this scheme.
Yep. And there is a slight difference in delays coming through here. So when you put it on a normal monitor made by somebody else, you'd see a color fringe. Our 1701, 1702 monitors changed that timing back to be lined up. So even the monitor was part of the game we played, making the color look good at home. So it was a combination of the computer put out a signal a certain way, and the monitor made it into a good-looking picture. So let's see if there's a section I skipped over too quick or missed. I'll expand these if we saw that. I think we've gone over the entire Commodore 64 here in a nutshell, sort of. Ferrite beads, love them.
This might be more a question for Johan or someone like that in the group. But just always curious to me, how did software developers work with the memory mapping in the C64 with the full 64K of DRAM versus your character ROM, the kernel ROM? And I imagine that user programs were able to access all of those ROMs and use routines in them or data out of them when needed. Or was all of that stuff?
The guys that programmed the VIC chips were magicians in their own rights. They learned all the little tricks of how to. It's like the demo scene today where they learned how to do the tricks of the bugs. Well, we didn't back then. We just did the tricks. We weren't trying to do the bugs of the C64 because we wanted something that worked every single time in millions. So I'm just looking at the comments here. Somebody said Atari may have done a separate Chroma Luma. They may have. I'll confess an ignorance of the competition. The Atari also had more colors than 16. I want to say the 400 and the 800. But I'm a Commodore guy, so I need somebody else to answer that for me. One thing
Means is saying we swap out D000 to E0000.
Yeah, D0 is where the I/O lives, and E0 was the start of kernel ROM.
Yeah, so you could, Kurt's saying you would do a copy copy some kernel ROM to RAM and then execute it from there, yep.
So we did things, and you can't see this on this one. I was looking for the IO chip select and the I'm looking for there it is.
There would have been pretty well-known routines, assembly language routines that the community would have used.
Oh yeah, the kernel did a lot of it for you too. Yeah.
Yeah, to switch things over and do bulk copies into RAM and then jump to RAM to execute from there, and all those normal things that you get from an operating system these days was done from the kernel ROM.
Here's the final part of the Commodore 64 is the programmable logic array, the PLA, not a PAL. PALs were little 16 to 20 pin programmable array logic, and they did an and/or array or an or-and array. I can't remember which.
Yeah.
But the PLA did and/or array.
Yeah.
So this started out as a part from Signetics called the 82S100, and we reverse engineered it. I know that because I walked in the chip lab, and right there on the wall are these Polaroids taken through a microscope of the 82S100. So they did around the edges and all the control logic, and then part of the array. And we made our own version of the PLA. And shame on us, but we made millions, doing it. Our PLA had a problem. It got what we called the purple creeping crud. And so Commodore went through a period where we had real poor, they failed after 6 months. You take one of these chips, you take the cap off, you put it under a microscope, and it looked like fungus eating at it, like mold or mildew. And it was actually purple under the microscope where it got under the passivation layer. And I used to think it was due to the geometry of the passivation layer. Think of it as a glass coating, silicon nitride. Well, it turns out there was too much boron in the silicon nitride, and it contaminated it. And so we were making parts that only had a shelf life of 6 months, 7 months. Shame on us. We figured it out. We fixed it. Meanwhile, we kept shipping products. Got to ship product, dude. Got to get it out there. And so this guy does the CAS-RAM. He does the interpretation of these signals. Here, let me move the mouse. Low RAM, high ROM, CAS, which means the memory is being selected, character ROM, and the address lines here, and whether it's a read or write cycle, and then these XROM and game signals from the cartridge port. And from there, we generate all the chip selects. So this was a magic part. This determined when the CAS would go, as we said. It was part of, unfortunately, it was part of a timing equation that I wouldn't have liked it to be. But then it also drove the IO select, which we could see. Look at this. We bring IO select out. We add A11 and A10, and that gets us our VIC chip select, our SID chip, our color, and then we run out one more line, and that gave us our CIA and CIAH selects, as well as the selects out to the expansion port. So that's kind of rounds the horn. That takes us to where it's actually getting selected by the processor. So there's a Commodore 64 in a nutshell for you. Oh, my throat's sore now.
Well, I'm glad my voice is almost back to normal, but I'm still recovering from that illness I had a couple of weeks ago. When my voice was croaky when we were doing the Roland teardown. It wasn't exactly a teardown. I didn't tear it down. I don't want to tear it down. I want to use it, but yeah.
Right. Somebody posted about 01 and 00. That's that 0 port that was on the 6502 that made it a 6510. 00 was like the register, and 01 was the direction register. So when I say the full 64K, there was always 2 bytes taken out of that to control it, so you could get in and out of the 64K if nothing else.
Yeah.
Yep.
Very cool.
So Commodore 8526 had 2 PLAs that ran similar. What is that? 8920. I don't know what an 8296 is. So any questions real quick before we wrap up from the chat channel? I know I went fast. I'm hoping you could see the schematics. I love Zimmer's. If he ever goes off the web, I don't have copies of these. There'll be an enormous loss to the community, though I believe somebody said it is mirrored in some places.
Yeah. Just some comments about the PLAs tend to be unreliable from the earlier ones, and a lot of
Right.
people have done replacements on those.
The Micron DRAMs. Okay, so let's talk about DRAMs real quick. We abused the DRAMs, right? But at the same time, the DRAMs had problems too. They were brand new. And we ended up suing Micron DRAM because we said they're not working our circuit. Well, you know what? They failed more often in one of the locations than the others. Well, that tells you it's also about how you use it. And so it was a little bit of both. It was half how we're using it, and it was half Micron. And we sued Micron, that Micron sued us, and then I believe we came to an understanding because we bought the Micron DRAM process. We tried to make our own DRAMs using Micron, and we had problems with the polygons in the mask level. I remember the guy going, we can't converge the corners on these polygons, and we called them, and they said, yeah, we had the same problems. So we bought their problems.
Did it end up working though?
I don't think we ever. I don't remember a Commodore DRAM that worked. I don't. I'm not saying we didn't. We did try to make our own TTL too, and you can only use them in certain places because they weren't true TTL compatible.
Yeah.
So we want new SIDs. I second that. Yes. So everybody, if you've seen this show and you did not see the New Year's Eve show, look in my channel for the New Year's Eve show, or Google FPGA Commodore 64. The SID chip is one of those chips that's being replaced, as are everything from the 6502 to the VIC chips. These are 40 years old. So it's amazing any of this works, especially the Commodore 64, since we did have some production problems with the 64 right out of the gate. Nobody had made millions of this stuff before. I mean, even the Apple and stuff, they made 1 million, and we're blowing by them 5, 6, 7, 8, 9, 10 million. We're just pumping these things out.
Brilliant.
So, are you ending the show now? Tell us some stories from your Commodore days, preferably serial related. They're always fun to hear. I am ending the show now, Andreas. I've been trying to sprinkle in the stories. Buy the book. The stories are in there. I hate to plug the book, but
so the book's a lot of work to write a book. You've got to support it.
So there are some stories. If you Google me, my VCF talk was up there. Pretty much all the stories are in there except where the wire came from, because I ran out of time. So Google Bil Herd VCF 2021 or
and also
whatnot.
Come back. Well, like we do this every week, so you know what? We've got to save something for future shows. So come back.
So, the conversation Ben and I had was we could go through Zimmers and talk about disk drives, talk about the monitor schematics. I got that idea from Joanne was trying to fix his monitor. He got it fixed actually, and I looked, and sure enough, the schematics are up on Zimmers. And so, what's a monitor? Well, it's a fancy word for a TV set, but I can show you how to fix your monitor, or at least tell some things about your monitor that you may not have known. Like, for example, the heater voltage that makes the back of the tube light up, that doesn't come from the AC line voltage. It comes from the flyback. It comes from the high voltage. So we actually use 15 kilohertz to light up that filament in the back of the picture tube. There's cool stuff like that built into it.
Lots of tricks. Lots of tricks.
So
thanks,
make
Bill.
sure. Yep, I'm just reading some comments. Oh, this is my pleasure. I've been wanting to do this and never thought that we could do it here. And lo and behold, we gave it a run. We gave it everything it's worth.
Yeah, and there's still so much to talk about.
So
thanks everyone for joining us. We have 125 people live now. That's, I think, as many as we've ever had.
Yep. So and hopefully you got out of this, what the reason you joined was hopefully you got to see some stuff about the schematic, maybe hear some old stories. Join us again. I put the Discord invite at the very top of this. Join us and ask questions during the week, and we'll try and answer them. Tag me too if you especially want my attention. Tag me or Ben in the channel, and that definitely gets my attention then.
Yeah,
maybe not the same day, but.
We're not the only experts around here. A lot of people who watch this and who join us on Discord and who sometimes join us as there's some really amazing gurus in the community who can answer questions too. Especially
the third-party stuff. You know, I left Commodore in '86. People will ask me about stuff that got added later. I don't know anything about it. I wasn't there anymore. So you guys, a lot of times, know more than I do about how the stuff actually got used, especially late 80s into the 90s. So, well, thanks, everybody. Thanks, Ben. It was wonderful yelling at everybody, just talking my ass off here.
It's so cool.
So,
great. Yeah.
We'll see everybody next week. Yep. Thank you, Ben. And we'll see everyone next week.